Alright, so this is the beginning of chapter 2. We're going to be looking at kinematics. Kinematics is the study of motion. So kinematics describes motion. We'll use this in this chapter, of course. In the next chapter, where we'll do two-dimensional motion. This chapter will look at just one-dimensional motion. That is motion either in the horizontal or vertical directions. And the next chapter will look at the motion of objects as they move through two or more dimensions. Actually, we'll just do 2 dimensions. But we'll use this all throughout the semester and even into next semester. So it's very important that you get it now, because you're going to use it a lot in the coming months. Whenever we look at kinematics problems, we need to consider a frame of reference. When we consider the frame of reference, that is, we will set the coordinate system. Now, first of all, asking the question, what kind of coordinate system will I use? Will I use a Cartesian coordinate system, that is a rectangular coordinate system, or will I use a plane polar coordinate system? Now, in these first couple of chapters, we're going to use just Cartesian or rectangular coordinate systems. But in a later chapter, when we look at rotation and torques and what have you, we'll use the plane polar coordinate system. So we set the coordinate system and the origin. That is, we define what we call 0. And then also ask the question, from where are you observing the motion? So for example, are you observing the motion from a stationary point in space or from a moving point in space? So let's say I see a car traveling down the road. If I'm standing on the side of the road, that car is going to appear much differently than if I'm driving in a car going in the opposite direction. So we'll get into that a little bit with relative motion. Now in kinematics, we consider 3 different things. We consider the displacement. We consider the velocity, that is the rate of change of the displacement, and the acceleration. And the acceleration is the rate of change of the velocity. In this first section, we're just going to define these 3 things, displacement, velocity, and acceleration, and also learn how to interpret graphs that show these physical quantities. So first of all, displacement is just a change in position, where we say our displacement is just x final minus x initial, where xf is just my final initial and xi is my initial position. I don't have the Seabiscuit clip actually. I might post one on YouTube, we'll see. But let's imagine that if I have something that's moving around a track, so I have a horse, and it gallops around the track, going all the way around. Now a track is about 1 mile. I think a track is 1 mile actually. So while this horse might have traveled 1 mile, the actual displacement of the horse is dependent only upon its final and its initial position. So it starts here and it ends here. So if I start and begin at the same place, my displacement in this case is going to equal to 0, because my final position is equal to my initial position. So let's say, for example, let's say I have this point, and I'm going to call this x equals 0. All right, and then I'm going to mark out some 1 meter increments. We'll say that these are 1 meter increments. So I have 1 meter, 2 meters, 3 meters, and then over here I'm going to mark out 1 meter increments over here as well. So I'll call this 1 meter, 2 meters. That is just 2 meters from that central point of x equals 0. All right, so this is my origin right here. Now let's imagine that I start at a certain point. Let's say that I start over here, and I move in this direction over to this point. What is my displacement in that case? Well, my displacement in that case is I moved from 2 to 1, and actually I'm going to call this -1, -2, and -3 because it's to the left of the 0. Remember, in our Cartesian coordinate system, left is negative. So in that case, if I wanted to know what is my displacement, delta x, I would say that it's delta final. My delta final is -1 minus delta x initial. So x final minus x initial. So -1 minus 2, which is equal to -3 meters. So in that case, my displacement was -3 meters. Let's say, for example, if I start here at -2 and I go to 1, what is my displacement there? Well, delta x, which is my displacement, is x final minus x initial. And my final position, I said, was at the 1 meter mark, minus my initial position, which was 2 meters. And so that's 1 minus a -2. And so that displacement is now 3 meters. So I have two displacements here, one of which is positive and one of which is negative. And that becomes important because displacement is a vector quantity. And vectors have both a magnitude and direction. They have both a magnitude and a direction. So for example, up here, when I had delta x equals to -3 meters, that was right here, the direction is given by the negative, and the magnitude is given by the 3. So the number here represents the magnitude, and the sign represents the direction. Now remember, what is a negative direction in our Cartesian coordinate system? Well, we say that it is left. If we go back up here, remember on my displacement, my final was 2, and my final was -1, and my initial position was 2. So I was starting here and going over to -1. So notice that I moved 3 meters, 1, 2, 3, in the negative direction. And so that's what that vector means, that the sign means on our displacement. Now sometimes we give direction in other ways, and we'll use those here. We'll use north, south, east, and west. All right, we'll use those actually in the next chapter to give two-dimensional vectors. We can use up. Oh, actually, let me go back here. So for these, north is going to be positive, south is negative, east is positive, and west is negative. So if I were to draw these on a Cartesian-like plane, it would north, south, west, and east. So that's sort of like a normal Cartesian coordinate system. We'll also use up, down, left, and right. Up, down. So where up is positive, down is negative, left, and right. These are all used to denote the direction, where left is negative and right is positive. And so you'll see this in some of your problems, where instead of giving, in the x direction or in the y direction, the direction will be given as left, right, up, down, north, south, east, or west. All right, there are a number of different examples of vectors. All the three kinematics quantities, displacement, velocity, and acceleration, are all vector quantities. There are some other vector quantities as well, such, for example, as forces, momentum. We'll get into all these. These are derived from these basic kinematic quantities. We usually show the variables for vectors with an arrow. So for example, with displacement, velocity, and acceleration, we just show them like this. Now, in contrast to vector quantities, scalar quantities only have a magnitude. So what are some scalar quantities that you consider? These are quantities that do not have a direction associated with them. Well, for example, mass, that doesn't have a direction associated with it. Temperature, volume, area, those sorts of things. We'll also see that displacement has a scalar counterpart, and we're going to call that distance. So for example, your car has an odometer on it. That doesn't measure displacement because it has no notion of direction. Or excuse me, it doesn't measure displacement because it has no notion of direction. It only measures distance. Likewise, your speedometer doesn't measure velocity because it doesn't give the direction. And so the scalar counterpart to velocity is going to be speed. And acceleration doesn't really have a scalar counterpart. All right. So distance and speed are the scalar counterparts to displacement and velocity. Okay, this quick test is not really placed well here, but we will come back to it. And you'll see it in the online quiz, but you don't really have the information you need to work this right now, so just hold off on it. However, you should be able to answer this. Which of these is or are scalar quantities? All right, now, as I said before, speed is a scalar quantity. It is the magnitude of the velocity. And we have a couple of definitions for speed. Average speed is just the total distance divided by the time. Or we can write it more simply, just v is d over t, the distance over time. So for example, if a runner traverses a 400-meter track in 60 seconds, actually let's say 40 seconds just to make it easier. If a runner traverses a 400-meter track in 40 seconds, what is her average speed? I think the world record, by the way, is like 42 seconds. So if they do it in 40 seconds, that's pretty darn good. Anyway, so speed is the total distance, 400 meters over 40 seconds. What is his average speed? Well, that's just 40 over 4, or 10 meters per second. So what is the distance covered? Well, the distance covered is just the distance of the track, but what is the displacement? If I have this runner that starts here and goes around, my final and initial positions are the same, so my displacement, which I'll call, let's see, I'll call it I'll call it d, but with an arrow over it, my displacement is equal to 0. Well, this is my distance. See, the difference there is that I haven't drawn the arrow on the d, and so it's like the scalar counterpart, or the magnitude of the vector. So the displacement is 0. Likewise, the velocity over that time is also going to be 0. But we'll get to that in just a moment. What comes up next, actually? The average velocity. This is a vector quantity, so it should have an arrow over it. The average velocity is delta x over delta t. All right, where this is a vector quantity. You could also write this. I'm sort of using x and d interchangeably. You could write it delta d over delta t. Either one is okay. Xf minus xi all over tf minus ti. All right, remember, this is the definition of displacement. That's the definition of displacement. So average velocity is a vector. And so, of course, it has both magnitude and direction. And so the question I asked previously, what is the average velocity of the runner in the previous problem? Well, since the final and initial positions are the same, then the average velocity is equal to xf minus xi, which is going to be 0 minus 0, because his initial and final positions are the same, divided by 40. So his average velocity is equal to 0 meters per second. This comes up a lot when we're looking at plots. So for example, in this plot, say I have this plot of position versus time. The slope of the line gives the average velocity over the interval from, in this case, from 0 to 30 seconds. 0 to 30 seconds just because it starts at 0 and the line stops at 30. So I could find my average velocity here. Let's see, I think it's on the next page. Let me see. So if I want to find the slope here, it's going to be delta x over delta t. Remember, this is the same as the definition for slope, rise over run. Rise is my x or y, this axis, and run is my t-axis, my time axis. So if I look at delta x, it's going to be 40. That's the position up here, minus a negative 20. Divided by 30 minus 0. And that's equal to 2 meters per second. So that is my average velocity, and it's equal to the slope of this line. So the slope of this line is 60 over 30. Rise over run is equal to 2 meters per second. The slope of a position versus time graph gives the velocity. Let me write that out in words. Slope of position versus time gives velocity. And in that quick test, you have to do that. You have to find the velocity by finding the slope at a particular point. There's some caveats to this, or not caveats, but some added complications. We'll see. Now in this case, because the line is straight, that means, the slope doesn't change. Because the slope doesn't change, then the velocity also doesn't change. And in that case, the average velocity, say, for example, from 10 to 30 seconds, is the same. So if I were to calculate this, just taking a different time interval, instead of from 0 to 30, I'd take from 10 to 30. Delta x over delta t. Let's see, that's going to be 40 minus 0. Go back and look at that graph, and you'll see that at 10 and 30 seconds is 0 and 10 meters, respectively. All over 30 minus 10. That's my time interval. And that's 40 over 20, which is 2 seconds. So what I've done here is I've just calculated the slope using different points. But because it's a straight line, the velocity doesn't change. The average velocity doesn't change. Now in this graph, the velocity of the object varies with time, so the average velocity depends on the chosen time interval. So for example, if I take from 0 to 10 seconds, then that's going to be 30 minus 20. Divided by 10 minus 0. And that's equal to 10 over 10, or 1 meter per second. So what I've done there is I've just found the slope of this line right here. However, if I take a different time interval, say from 10 to 30 seconds, I'm going to draw it here and then I'll go to the next page. Say I want to know the time interval from 10 to 30 seconds, then I'm going to find quite a bit different average velocity. So from 10 to 30 seconds, it's going to be minus 20 meters minus 30 divided by 30 minus 10. And then that's going to equal negative 5 meters per second. Okay, so average velocity, and now we also have instantaneous velocity. Now, the velocity, when we draw it like this, that's going to be our instantaneous velocity, and it's the velocity at a particular time. An instant of time, and that's where we get the word instantaneous. That is the velocity at a particular instant. A speedometer in a car. For example, gives the magnitude of the instantaneous velocity. The instantaneous speed, if you will. So it gives you the velocity at a particular instant in time, that particular instant of time. Now, the instantaneous velocity is defined as this. Now, you're not required to have had calculus, but many of you have, so I'm going to show you this. The instantaneous velocity is the limit of the average velocity. This is just the average velocity as delta t goes to 0. And so you're letting the differential element of your time get very, very small. And that, of course, is the definition of a derivative. And so v, then, the instantaneous velocity, is just the derivative of x with respect to t. And again, you're not responsible for that, but many of you have had calculus, so there you go. In fact, calculus was largely formed to study kinematics in that way. Now, in a nonlinear graph, such as this one, the one on the next page, the slope of the tangent line is equal to the instantaneous velocity. So for example here, let's say I take a point here. When I say the tangent line, that means a line that is tangent to the graph at that particular point. Now if I look at a tangent line here, the slope of that line is different from what it is up here. The slope here at this point is smaller than the slope here. So I can see that this graph shows an increasing velocity. It has an increasing slope. Or I can think of this instead, and you should think of it in this way, an increasing velocity. We'll see a number of different questions where you have to interpret these position versus time graphs. Remember, the slope of the position versus time graph gives us the velocity. All right, here is a quick test. You'll find that on the online quiz and a similar one here. We will stop there and pick up in a bit.